Welcome back. Now we'll take a look at the conduction of the cardiac muscle itself and look at the processes of getting that electricity through the heart. So when we look at the heart, you may remember from anatomy that the heart, in a sense, kind of has two different portions to it. It has contractile muscle cells, and then it also has the autorhythmic cells. And so, in all reality, all of the cells that are within the heart have the potential to be autorhythmic. We could, in a sense, take some cells out and put them in a petri dish, and they would sit there and contract all on their own. And they would eventually start to come into a rhythm that is the same with each of those cells as well. So, they have this potential to self-generate an action potential. And so this comes down to a little bit of the processes that occurs within the cells as far as their sodium channels, but that's something we'll talk about a little bit later on. So they have that ability that we talked about in muscles as far as their autorhythmicity, that they are myogenic, and so they have the ability for the muscle cells themselves to generate their own action potential. They don't need that electrical impulse from the nervous system in order to start it. But the majority of the cells, the overwhelming majority of the cells that are in the heart muscle itself, don't do this on a regular basis. And so the majority of the cells are under, in a sense, kind of the control of all the rest of the cells that are the actual so-called pacemaker cells, the cells that are actually going to do the process of generating that electrical activity with each contraction that is occurring there. So the majority of the cells are actually contractile cells. These are the ones that are going to allow us to have the contraction of the muscle. They're going to squeeze the muscle. They're going to squeeze the blood out of the heart itself. So where we have these autorhythmic cells are in some very specific places within the heart itself. And so again, back to the anatomy of things, we had two special areas where we found these nodes. And so we had a sinoatrial node and we had an atrioventricular node. This sinoatrial node and atrioventricular node were the two places where we were going to start this process of action potentials forming within the heart itself. And so we saw them up there in the right atrium, sitting there. That information then traveled from the AV node down to the bundle of His, and then down through the Purkinje fibers. And so this allowed us to transmit the signal all the way from that right atrium through to the left atrium, come down into the ventricle, but instead of working from essentially the top down towards the apex of the heart, we worked that electrical signal came down through the interventricular wall and then came down to the apex and then worked its way back up through those Purkinje fibers and allowed for that contraction to basically squeeze from the apex back up towards the base of the heart. And so that electrical potential as it sits in the heart itself, if this is kind of my heart here, that electrical potential is then traveling rather than through the walls down through the interventricular septum and then back up the outer walls of the heart. And so our squeezing of the heart is going to end up moving back up towards the top that's there. And after each action potential has occurred, one of the things that allows it to be having this kind of autorhythmicity and kind of starting to set its pace there is the fact that the next action potential is basically being triggered by the previous action potential. And this is because there are some special sodium channels inside the heart that are actually called funny sodium channels. And so when they were discovered and they were found, they weren't quite acting the way that the normal sodium channels were, and so they were kind of funny and the name kind of stuck. And so funny sodium channels essentially are going to open up when that, if we were to kind of follow the voltage of a depolarization, and it goes up and then comes back down. And when we get into that repolarization phase, those sodium channels start to open up. And so they're, rather than essentially closing like we would normally have our sodium channels close up here, those sodium channels are actually starting to reopen during the repolarization phase. And as that occurs, once we get back down to a resting potential, those are going to be opened enough that they're going to allow for the next action potential to begin. And so kind of a different process from what we saw when we looked at skeletal muscle. So when it comes down to it, we really have kind of two different types of tissue going on inside the heart muscle, even though it is all heart muscle. And so we have our SA node, and we have our AV node. And then we have our special bundles of fibers that travel from the AV node and down through the interventricular septum. We have our bundle of His, and then back up through the walls of the ventricles, we then have our Purkinje fibers. And so we have this electrical system within the heart that's going to send the action potential through the heart. And so it's going to begin over here in the SA node and then into the AV node. And those are our primary autorhythmic cells that are within the heart itself. The rest of the cells are all just contractile cells. They are doing the same things. They look the same as what we saw for normal cardiac anatomy. And so they're branching cells. They're typically single or maybe double nucleated cells. They have our intercalated discs in between each of the cells, and so we have our ability to have all of our gap junctions and everything in between those cells to be able to send the ions from one cell to the next and propagate that action potential all along the way. And so everything else kind of looks the same. It's those conductive cells. It's the cells that are our cells that are there for the action potential that are slightly different compared to all the rest. So this system here is going to allow for essentially the atria to contract first and then the ventricles. And so the whole system isn't going to contract all at the same time. And so we're going to spread this electrical activity across the atria. The two atria are then going to contract. That's going to push our blood down into the ventricles. So we've got to get blood into the ventricles themselves first. And then from there, that electrical potential is going to travel from the AV node down through the bundle of His, back up through the Purkinje fibers, and then we're going to get that contraction of the ventricles, and then the blood can leave the heart itself at that point. And so this whole entire process relies upon the fact that we've got this electrical system within the heart and it's functioning. The thing of the matter is, in terms of those areas of electrical activity, is they don't all work exactly at the same natural kind of pacing and everything within the heart itself. And so they have kind of a little bit different process that goes on at each one of the different points. And so the SA node is our beginning point. This is essentially our pacemaker of the heart itself. And so in the upper part of the right atrium, we have the SA node. So this SA node is going to sit there, and that action potential, as I just said, spreads across the right atrium into the left atrium, and we get that action potential spreading across there. Once it comes down and hits the AV node, then it's going to start to move into the next portion of the heart. So the AV node is going to receive that electrical signal from the SA node, and it's going to have kind of like a delay switch in it. It's going to have the ability where it kind of has to be primed in a sense. And so the atrium has depolarized, it has started to contract, and that electrical signal is now sitting here waiting in a sense in the AV node. And so that electrical wave gets a pause at the AV node itself. And so we have this AV node delay. This is where our electrical activity is going to rest in a sense for a second. Not quite a second, but it's going to last there for a moment. And then that action potential is going to then travel down through the bundle of His, and then back up through the Purkinje fibers. And so this is going to give us kind of a momentary pause where the atria contract, they fill the ventricles with their blood. So we've got to get that blood into the ventricles first and fill up those ventricles, and then we can contract. So we don't want this process where essentially the AV node happens and then the ventricles contract instantly, because that would then lead to a less filled ventricle. So we want to give that ventricle time in order to receive, in a sense, all of the blood that it's going to need. So again, we start out at the SA node here. Our electrical activity travels through the atria. It comes to the AV node, and then we have our AV node where it's going to pause. One of the things that happens to essentially stop, so when you think about it, since all of these muscle cells have gap junctions in them and they're interconnected with one another, that electrical signal should instantly jump over across into the ventricles, but it doesn't. And that's because in between the atria and the ventricles, we have this little space here, which is going to, because red is a good color there, it's going to act as a stop for our electrical activity. It's going to stop it from coming into the ventricle from that point. So it's not going to make it across. It's not going to continue across into the ventricle. And at the same time, if it did that, then our wave of electrical activity would be traveling down towards the apex. And so the upper part of the ventricle would be contracting first and then down at the apex. And we don't want that. We want it to squeeze from the apex up towards the base. And so we'll make it move up towards the other direction. So that connective tissue, that fibrous tissue that's in between the atrium and the ventricle, stops that process. So now we have our electrical activity paused here in the AV node. Now it can come down through the bundle branches, come up the Purkinje fibers into each ventricle, and then we can get this wave of contraction moving from the apex up towards the base. And now we have this contraction of the heart muscle itself. The thing about it that I mentioned before is that the cells themselves don't all contract, in a sense, at the same base rate. And so the SA node wants to have a heart rate in the neighborhood of 70 to 80 beats per minute. And so this is where it's going to send off an electrical activity. So if we took some cells from the SA node and again put them in a little petri dish, we would see them contracting at about a rate of 70 to 80 times per minute. The AV node slows down a little bit. The AV node wants to contract at a beat of somewhere in the neighborhood of 40 to 50 times per minute. So we're slowing things down. We're going to slow things down a little bit further as we move into the bundle of His and the Purkinje fibers. Now both of those are down in around 20 to 40 times per minute. And so the different areas of the heart have different kind of natural contractile rates. But that being said, that doesn't mean that the SA node is firing off at 70 to 80 times per minute, and then the AV node is 40 to 50 times per minute, and then the bundle of His and the Purkinje fibers are 20 to 40 times per minute. Otherwise, we'd have essentially the SA node, say, with a rate of 75 beats per minute, and then we'd have for the atria, and then down in the ventricles, we'd end up with a rate somewhere in the neighborhood of, say, 25 beats per minute. So that would mean that the atrium is contracting 3 times for every 1 time that the ventricle is contracting. And we definitely don't want that. We don't want to see that disconnect between the two. And so essentially it becomes the SA node that controls the pacing. And so the SA node is setting that pace all the time. It's the one that is going to, in a sense, kind of override these areas. And so that's going to set the pace of the entire heart itself. And that's going to travel from the SA node to the AV node, to the bundle of His, and then to the Purkinje fibers. That's where we get our pacing from. If that electrical activity does not happen the way that it's supposed to, and so if we end up having damage in an area, say up after, just after, so we have the SA node up in here, we got the AV node down here, and then got our bundle and our Purkinje fibers. If we create an area where we have damage in the electrical activity somewhere, and that causes a change in the ability of those fibers to send off their signal, we're going to have a disconnect. And so this is where now, since the SA node wants to go at, say, 75 beats per minute, and it's sending its signal, but it's being blocked just after the AV node. So in terms of the AV node, its signal isn't getting through. The only thing getting through basically is the bundle of His and the Purkinje fibers. And those wanted to travel or send off a signal somewhere in the neighborhood of 20 to 40 beats per minute. And so those contractions that are there are going to be less. And so if we were to hook that person up to an EKG, we would typically see their rate being, somewhere, kind of take the middle road. And so we're going to have 30 beats per minute. And those 30 beats per minute is what we're going to see. But the atria may actually be in the same 75 beats per minute. And so we're going to have a dysrhythmia. And so we don't have a good rhythm in the heart itself. And so they're not going to be able to send the blood when they need it. And especially since the ventricles now can only beat at 20 to 40 beats per minute, if we do something like go from laying down to standing up very quickly, we've got to increase our heart rate. So our beats per minute need to go up in order to combat the change in gravity. So we've got to change that's there. So in that case, a person is going to need something like a pacemaker. And so the pacemaker is basically going to circumvent that disruption in the electrical activity. And we see where the electrode here comes into the heart, and it's going to create that electrical activity at the normal pace that we should have. And so there are different kinds of pacemakers. Some pacemakers even have a internal defibrillator, and so it can alter the pacing that is there when needed. If it gets out of pace in terms of the two sides of the heart itself, it can have single leads, it can have double leads, all depending upon where the damage is and what the damage is. But the whole idea of the pacemaker is that it realigns the pace between the SA node and the ventricles, so that they're going to have the same pacing every single time that the heart contracts. That pacing normally is in terms of the cells and how they contract. We've seen before that when we look at those intercalated discs, inside those intercalated discs we have things like gap junctions to allow for all of our sodium ions to be able to move from one cell to the next. And so we have all of these gap junctions here in between that intercalated discs that allows for it to move from one cell and keep on moving that sodium and move it into the next cell as it moves along. And so we're going to instantly be able to move that electrical signal from one cell to the next, and one cell to the next, and one cell to the next, every single time that we have a contraction that's there. And so those gap junctions are an important aspect for that movement of ions, our sodium and our calcium ions from one cell to the next. Remember that calcium is going to have to move through there as well because it doesn't have as well developed of a sarcoplasmic reticulum in order to get those ions to move from one cell to the next one. And then just a little microscopic view of those same things. We can see our intercalated discs here. in between the cells themselves. They're obviously striated. They look like a normal striated muscle that's there. They're branching. This one happens to have 2 nuclei inside the cell, and so on. So we have kind of the same basics of the heart itself. And next up, we'll start to look at those muscles actually contracting and how we get that contraction through the heart itself.